So this week's tutorial is basically based on homework number 7. So homework number 7 is, the solutions that is already uploaded on under the week 8 section, right, on your Moodle.
Yes.
So this week's problem is basically based on, it's pretty much simple. It is mostly based on attenuation, rain attenuation, and the Fresnel zone. Right. So we have a total of, I think, 1, 2, 3, I think 4 questions altogether. I think. Yeah. So let's start with the first problem. The first problem says, find the Fresnel zone if the communication. Oh, sorry. The same question? Oh no. Okay, this is the first question. So find the attenuation due to rain, right, in dB per kilometer. If vertical polarization is used in a WLL link in a climate region H, where the link is available 99.7% of the time. Operation frequency is 30 kilohertz, right? So based on this, um, this is the formula that we need to use. That is basically attenuation is equal to A times R to the power of B, where A and B are the coefficients, right? Vertical polarization coefficients, where R is actually the rain rate. So you can basically find this formula in your textbook if you need to know more about this particular formula. It's in your textbook, right? Over here, you can. It's on page number 339, right, of the textbook. I have already passed on the textbook, so you can check that out, right? So basically, the attenuation is basically given by A times R to the power of B, where the A and B depend on the distribution of the drop sizes and on the frequency, right? So it is basically the drop size, the parameters for the drop size distribution and the frequency distribution. And R is the rain rate. So for this particular problem, we'll be using this particular table over here, right? So for a set of, for a particular frequency, the horizontal variable A, the vertical variable A, while the variable for B, the horizontal component of B and the vertical component of B is given over here. So, like the question says, that we'll be using a vertical polarization. So we'll be basically using the vertical components of A and B variables, right? So we'll be basically using AV and PV columns over here. So this will be our coefficients for A and coefficients for B. So how do we determine which column to use? So we'll go back over here. Oh, no, we can directly determine from this, right? So frequency is 30 kilohertz, right? 30 gigahertz, right? So our frequency is 30 gigahertz. So we find corresponding coefficients for AV and BV because we are using vertical polarization. So our A value will be 0.16 and our B variable will be 1. So knowing these two variables, right? What else do we know? We know these two variables, right? So we know the coefficient AV and we also know the coefficient BV. So we also need the rain rate as well, right? So our rain rate is basically again going to be coming from the table, right? But this time, in order to calculate our rain rate, we'll be using this particular table. I think so. Yep. So the table is in the next page over here, right? So we'll be using this particular table over here for our rain rate. So you can see that this particular table has a set regions, right? So there's A, B, C, D, E, F, G regions over here. We'll based on the question, we'll be basically conducting the analysis for H region, like it says, right? We are basically focusing on the H region, so we'll be basically focusing on this particular column, and then we have to determine the outage percentage of time, right? So based on this, we can determine what parameter to use for our rain rate, right? So we either to use two, right? So in order to determine that, what we do is we go back to our question. The solution set, you can see our availability is for 99.7% of the time. So the other rest, the remaining 0.3, 0.3%, right? Because the total will be 100%, right? So either it is available or it is out. I mean, it's not available. Both together will give us a percentage of 100%. So what we do is we find the percentage for outage. So outage is basically given by 100% minus the availability, right? Which is equal to 100 minus 99.7%. So in that case, 0.3% is our outage. So then we go back, we know our outage is 0.3%. We go back to this particular table again, right? In this particular table. Now at 0.3% outage range, and we are in rain climate zone H, right? So the parameter for that is, this is the second row and this particular column. So we'll be basically using 4 as our rain rate. So 4, so we'll be using this particular variable, and it will be, the rain rate will be in millimeter per hour, right? So the unit of this rain rate is basically millimeter per hour. So so we know our rain rate. So our rain rate is basically equal to 4. And our availability factors, the availability coefficients A and B are, for the vertical components, are basically 0.167 and 1, right? So knowing our A variable, knowing our B variable, and knowing our R variable, we can calculate our attenuation. So directly substituting all the values into this particular formula, our A value, the B value, and the R to this particular formula, that gives us A is equal to 0.167, right? 0.167 times 4 to the power of 1, which is equal to 0.668 decibels per kilometer. Okay, so is that fine? Do you have any questions regarding this? Okay, so yeah, we move on to question number 2. Question number 2. Find the first Fresnel zone if the communication link is to be established between a user and a service provider if the link is in line of sight over 10 kilometers. The consent point is an historic tree located 3 kilometers from the transmitter antenna, and the operation frequency is 15,000 megahertz, right? So we know our frequency, we know that the total distance is 10 kilometers, right? So the distance between the transmitter and receiver is 10 kilometers, right? And the tree is actually located 3 kilometers from the transmitter, right? So you can draw, if you draw a free body diagram of this representation, whatever information is given over here, you'll get something like this, right? So at the one end, you'll be having your transmitter, at the other end, you'll be having your receiver. And the tree is actually located 3 kilometers from the transistor, from the transmitter, right? So your tree is there. So now we have to determine, we have to find the first Fresnel zone if the communication link is to be established, right? So we have to basically find the best Fresnel zone. So Fresnel zones, there's many definitions. In my simple definition, I'll show it to you as this, right? Zone, right? So this is a Fresnel zone, right? We know about concentric circles, right? If you throw a stone into a pond, it radiates, isn't it? It forms a Doppler effect type, so it radiates. So similarly, a signal actually has many multiple parts of line. It can be sent into multiple ways, right? So it can radiate directly, right, in different directions. It can directly radiate as well to the receiver end as well, right? So basically, it spreads around, right? So then the communication line established like in that particular zone, right? So yeah. So if you just say that this is just a particular curvature of communication line, right? So if you say that this zone that it forms, right, by transmitting signals into this particular amount of angle, right? So let's say this amount of angle transmits, what do you say? The radiation angle of the signal is within this particular radiation, this particular range, or in this within this particular component, right? So that means it is within that Frenzel zone range 1, right? So this is the most immediate and most effective communication line, isn't it? Within this particular zone, I mean, like direct line of sight is the most effective or the shortest path for the communication to communicate, right? Um, there are other lines of communication, like no signal can also travel like this, right? In this particular angle as well, right? At some point, it will reflect back and come down. It can also rotate like this as well, right? So whatever, I mean, like it can bounce from an obstacle and come back. So there's multiple range of multiple ways of communicating to this particular trans. Let's say this is a transmitter, this is a receiver. So whatever signal that falls within this particular certain amount of angle is your best. I mean, like you can say each. I mean, like this particular angle, like the amount of angles can be divided into certain amount of ranges. So there'll be a first zone, there's a second zone, and then there's a third zone, right? So basically, there's different levels of zone. So the more effective line of communication becomes your first Frenzel zone, right? So within this particular zone, there shouldn't be any obstacle, right? So this within this particular line, I mean the first zone, this is the most critical zone, right? And then there will be a second zone, and then there's a third zone, right? So um, the angle of, I mean, the communication or the transmission angle will vary, isn't it? So with different variation of angle, the zones will change as well, right? So let's say the zone one is within this the transmission angle of 20 degrees or 30 degrees, right? So any angle less than this particular value, 20 or 30 degrees, is equal to, I mean, like falls into the first zone. Anything extra to that falls into second zone. So there is a certain amount of limits, right? So actually, that is just a simple way of explaining you, right? So actual definition of Frenzel zone is actually over here. Right? I'll show it in your textbook. If you go back to your textbook, that was just for your visualization, right? So I was first trying to like give you a fair idea to understand what the Frenzel zone is. So the actual definition of Frenzel zone is for effective communication, a millimeter wavelength. There should be an unobstructed line of sight between the transmitter and receiver. The question then arises as to how much space around the direct path between the transmitter and the receiver should be clear of obstacles. A useful criterion relates to the concept of Frenzel zone. The definition of Frenzel zone is based on the theory that any small element of space in the path of the electromagnetic wave may be considered the source of secondary wavelet, and that the radiated field can be built up by superposition of these wavelets. On the basis of this theory, it can be shown that objects lying within a series of concentric circles, so it's not concentric, it's not concentric circle, but rather it is a oval shape, right? Like I showed you, it's more of a oval shape. So it basically forms a concentric oval, you can say, right? So on the basis of this theory, it can be shown that objects lying within this around the direct line of path between two transceivers have constructive or destructive effects on the communication. Those that fall within the first circle, the first Frenzel zone, have the most serious negative effects. Like I said, in the first zone, the line of travel, or like, let me go back. Like I showed you over here, in the first zone, in this particular zone, you can see that in the first zone, let's say this is your first zone, right? It is made up of concentric circles, right? So let's say we do not know the boundaries. We just know that this is outlined as the first zone, and this outlined as second, and this is the third. So this is in a more also in an elliptical shape, right? So it forms more so in an elliptical shape. It forms a concentric circle type of behavior, right? So anything within this first uh, first uh, first zone is like in this particular zone the line of I mean the distance for communication is quite I mean there's the shortest path for communication, so there will be less obstruction, right? This is the more critical zone, right? So So yeah, so that is why it is considered so any obstruction between in this first zone is much more critical, right? So if there is obstruction in this, and there is high chances of destruction of signals, right? So that's regarding the fusel zone, right? So if you need to know more about it, like I said, the transmission has many part of communication. So it can go like in this direction, this particular direction, this particular direction. So you know how a signal actually radiates. However, the more effective one will be in the line of sight, right? So the direct path will be much more effective. So within this, there's a certain amount of angle, right? That it will, I mean, like let's say that amount of angle radiation actually falls into the first frontal zone. In the second, there is another set limit. In the third, there is another set limit of angle of propagation, right? Of this particular signals, right? However, in the first, I mean, as you go outside, any obstruction in the outer zones are less effective compared to the inner zones, right? So that's regarding frontal zone, right? So you get a fair idea of frontal zone, right? It is zones created like um, for obstructions. So anything that falls in the inner side is much more destructive, or it causes much more uh, obstruction to the signal being transmitted compared to the outer zones, right? So based on this image, you can just get a fair idea whatever the frontal zone is, right? I sure I like I was saying, right? Remember, there's multiple parts of propagation. So in the within this particular obstacle or in within a certain amount of range, you can say this is your best frontal zone. The outer layers can be having a different angle of propagation, right? So that's regarding your frontal zone, and your frontal zone is usually elliptic, right? That, that's fine. Okay,
Yes, sir.
great. So let's go back to the question. Right? I don't want to spend much more time. I like to speaking on the same thing over and over again. So let's just quickly go over this, right? So the frontal zone is actually given by R, right? So I mean, like the frontal zone radius at that particular point, right? So the frontal zone radius at this particular point, at let's say 3 kilometers. Oh, sorry. Frontal zone. Let's just quickly go back and let me tell you what the radius we are talking about. You can see since it's an elliptic shape, the radius will vary from point to point, isn't it? So at the radius of any object over here, it will have a different radius compared to the object over here, right? The distance from here to here is quite large compared to here to here, to the center, right? So that is why the radius of the obstacle in that particular part has to be different, right? So in order to know the radius at this particular point, right? The radius, I mean, just knowing that this is your center, right? The line of sight is your center. So from the distance between here to here, that is your radius, let's say, right? So the radius of this particular point over here is different compared to the point over here. So in this particular case, we want to know the radius at 3 kilometers over here, right? The frontal zone at this particular point, at 0.3 kilometers, right? So the frontal zone at this particular point, um, since it's a fresh frontal zone, so the fresh frontal zone radius is actually given by r is equal to root of lambda s times d upon s plus d. Your s is actually the distance from here, from this point to this point, right? From your transmitter to the obstacle, while your d is the distance from this obstacle to the receiver. Okay, so that's your d. Your s is from the transmitter to the obstacle. Your d is the distance from the obstacle to the receiver, right? So s is from here to here, and then d is from here to here. So that is for your first frontal zone. Just in case if you had frontal zone for the second layer, what you would do is this same formula will remain as it is, right? It remains as it is, but there's a multiplication of n inside this root sign, right? It has to be within this inside this root sign. So if the formula would have been n times lambda times s times d upon s plus d. So n is the nth frontal zone, right? Remember this n is the nth frontal zone. So let me write that over here. So you'll be having a n value over here, right? Let me read this. So that will be multiplied by n, right? So this whole inner function will be multiplied by n, where n is your nth Fresnel zone. So in this particular case, our n value is basically 1. So since n is 1, so this whole time remains as it is. So it is just lambda times s times d upon s plus d. So from here, we know our lambda, we do not know our lambda value. So in order to calculate our lambda value, we know the frequency and we know the speed of light. So lambda is basically equal to speed of light divided by frequency, right? So that would be speed of light is 3 times 10 to the power of 8 divided by the frequency, that is 15,000 megahertz. So basically 15 times 10 to the power of 9, right? So that is equal to 0.02 meters, right? So that is our lambda value. So our S value, like I said, it is the distance between the transistor, transmitter to the obstacle. So S is basically equal to 3000 meters. Our D value, since the total distance is 10 kilometers, and the obstacle is the distance between the transmitter and the obstacle is 3 kilometers, so the remaining distance is 7 kilometers. So our D value is basically 7000 meters. So the units of all the variables will be standard, right? So lambda will be basically in meters, and our S and D values will be in meters. So it is in standard units, right? So taking these values and substituting it into this particular formula, right? Into this particular formula, right? This is what you get over here, right? So you'll get a radius is equal to 6.48 meters. Just in case if you want to use S and D in kilometers, so your frequency has to be in gigahertz, and you'll have to multiply the whole solution by a factor of 17.3. So that will give you your radius in meters, right? Okay. So this is another formula, right? So, but in this particular case, we do not need to focus on this. We can use the standard unit formula, right? So just use the standard unit, right? So it is just lambda times 3 and lambda times s times d times n upon s plus d. S is the distance between the transmitter and the obstacle, and our d is the distance between the obstacle and the receiver. Okay. So once we know the radius over here in this particular case, right? We know the radius. Radius is basically equal to 6.48 meters. Now what we can do is uh, based on the IEEE um, the IEEE standards, right? So I'll show you that in a moment. So we know that radius at the radius of Fresnel zone at this particular point, at this particular point over here is of 6.48 meters, right? So now it says find the first Fresnel zone if the communication link is to be established between a user and the service provider, right? So yeah, now this is the radius of the first Fresnel zone. We know that, right? Now, with the what should be the maximum height of this tree, right? Before which it will start to obstruct the signal, right? So the transmitter and the receiver will be at a certain height, right? Let's say at a height of h, right? So the height of this transmitter and the receiver will be of h, right? A unit h, and the height of this particular tree is h. So our h is actually not given, right? So we have to find the maximum height of this tree before it starts to obstruct or cause major destruction of the signal, right? Before it starts to um, what do you say? It starts to cause errors in the signal, right? So we have to determine the height uh, of this particular transmitter and the receiver, right? So to do that, what we do is we go back to this particular book, right? To go back to our textbook. In our textbook, you can see over here, uh, right over here. Yeah, it's over here. So you can see over here, the IEEE standard is actually directly written over here. So one OT no example of an obstruction is hence the ground, hence the height of the two antennas must be such that there is no point along the path at which the ground is within 0.6 times the radius of the first frontal zone. So based on this particular standard that so it's 397, right? So based on this particular question over here, based on the standard, so the first frontal zone, so if the frontal zone, uh, sorry, the uh, the height of the antennas should be such that the objects or the obstructions should not be within 0.6 times the height the radius of the first frontal zone, right? So what we do is we know that it shouldn't be 0.6 times the radius of the first frontal zone, right? So in this particular case, what happens is we find 0.6 of the radius. So the critical zone, that is where the critical zone is, right? It is within the first frontal zone. We know it can cause errors to the main signal, right? So let's say this tree still falls within the first frontal zone, but what should be the height before it is much more critical, before which we cannot ignore the tree at all, right? So the critical zone is actually given by r times 0.6, right? So our radius is 6.48 meters. So the radius of the critical zone, so our critical zone will be, let's say let's say the first frontal zone is somewhere here, and like we have found the radius should be 6.48 meters. So let's say the frontal zone, first frontal zone is something like this, right? Of the antenna, and the radius at this particular point. Remember, this is an elliptical shape, right? So the height of this is, I mean, the radius of this from the center to the edge of this elliptical shape is 6.48 meters. The critical zone is r times 0.6, which is 3.89 meters. So, so the distance between, I mean, the line of sight is this straight line between the transmitter and the receiver, right? So this tree shouldn't be within 0.6 of this first frontal zone, right? So 0.6, that is 3.88 meters. So the critical zone is basically around somewhere here, right? So the critical zone is somewhere here, right? Within this particular line. So the inner elliptical shape, this is, let's say, our critical zone, right? And the critical zone has a radius at this particular point. Remember, this, whatever radius you have at this particular point, it is same. It is also reflected down as well, right? Remember, an elliptical shape is horizontally a mirror image, right? So it can be basically symmetrical about its horizontal axis, right? Depending on the orientation of the oval. So since the oval is in this particular horizontal line, or the major axis is actually horizontal, so it is actually symmetrical about its horizontal axis, right? So the frontal zone over here has a radius of 3.88 meters. So what should be the height of this particular tree before which we cannot ignore this particular tree? So let's say the height of this antenna is h, right? And the frontal zone, the critical frontal zone has a radius of 3.88. So our tree shouldn't be within 0.6 of this particular radius, right? So height minus 3.88 is the height of the tree that is, I mean, that is the maximum height of the tree which will not cause any obstruction to this signal that is being transmitted, right? So the maximum height of the tree should be around the maximum height, so that is given denoted by h, the small h, by subscript max is equal to the height of the transmitter and the receiver. So minus, so that is basically given by the maximum height of the tree is equal to the height of the transmitter or the receiver minus 3.88, which is the radius of the critical zone, right? So the height of the tree should be within this range h minus 3.88 before it will start to cause error to the signal that is being transmitted, right? So you get the idea of frontal zone? Zul, do you get this?
Yes, yes, yes.
So a Fresnel zone is that, right? So yeah, so it is basically a elliptical shape, a concentration of elliptical shapes, right? So the critical zone actually lies in this. So we have basically calculated the Fresnel zone radius at this particular point, that is 6.48, and then we have determined the critical region, right? The critical region is basically 0.6 of the radius, right? So that is 3.88 meters, and then based on the height of the transmitter, we have actually determined the height of the tree before it will, I mean, beyond which, beyond that particular height, the maximum height of the tree should be somewhere around H, the capital height, that is the height of the transmitter and the receiver, minus 3.88 meters. So it should be at that particular height at maximum. If it goes beyond that particular height, it will start to cause obstruction to the signal that is being transmitted, right? It will slowly reach much more closer to the line of sight, right? If it grows beyond this particular height, it will get more closer. If it starts to grow beyond this particular height, it will start to grow, I mean, come closer to the line of sight region, right? So it will start to cause more obstruction, right? So that is why the maximum height of the tree is basically given by this, right? So keep that in mind, right? Moving on to the next question. Our next question says the diagram shown in figure 1 depicts the transmission using the time division duplex. One of the ISDN defined interfaces provides a data rate which is equal to 384 kilobits per second and uses a frame size of 48 bits. If we use time division duplex with a block size twice the frame size, the distance between the subscriber and the network switch is 2.5 kilometers and the guard time is 0.5 milliseconds. Find or assume the transmission speed equal to speed of light. So we need to find, right? So we need to find a. This part is actually repeated over here, so I should have used this bigger part. Anyways, so this is the same thing that is repeated over here. So we need to find the best transmission time. So before that, I think I'll find this image. It's up here. Um, Transmission time, guard time, and burst time, right? So let's just change the diagram. Okay, this is the diagram that we are talking about. So yeah, this is a much more clearer diagram of here, right? So you can see, let me zoom in. Okay. Okay, so I'm not sure whether you can see this. Okay, this is the image, right? So let's say we have a base station and we have a handset. So the time needed for the signal to reach handset, right? You transmit the time, I mean, transmit the data at this particular station, and then you'll send that particular signal. So it will reach the handset after a certain amount of delay, right? So let's say there's a certain amount of delay. So you send the signal at this t is equal to 0 seconds, and then you get the signal at tp, right? So time for the first signal to reach to its destination is actually the propagation time, right? So we say this is the propagation delay. So you send a signal and then the signal takes some time to reach its handset or its destination. So there is some delay in the transmission of that signal that is being sent and received at the other point, right? So there is some delay. So that time is known as the propagation time. And then once the data starts to be received, right? Once you start to receive the data, the time for the first data that is being received to the, I mean, this is a particular block of data set, right? So this particular block of data will be having individual bits in it, right? So the certain, I mean, for that particular block of data that is being transmitted, the time for that particular block of data to be transmitted is known as the burst time. And then the time between the first block and the second block is known as the guard time, right? So it's basically propagation delay is actually the time for the signal, or it is the time for the signal, or it is the delay in which the signal that is being sent and received, right? It is the delay between the signal that is being sent and received. That is the time delay. So propagation time delay is TP, right? The best time is basically for the block of data to be transmitted from one end to the other end, right? The amount of time needed to transmit that set of data. And the guard time is that the time between two blocks of data, right? So that's regarding the propagation delay time, the burst time, and the guard time, right? That's given in your question over here. So it is not clear, so that is why I zoomed in to that particular image. So it says find the burst transmission time. So like I said, burst time is actually the amount of time needed for that set of bits to be transmitted, right? So the amount of time needed for that set of bits to be transmitted. If you go back over here, it says that the data rate is 384 kilobits per second, right? And then it says, and it uses a frame size of 48 bits, right? So the frame size is 48 bits. If we use the time division duplex with a block size twice the frame size, so each block is twice as many bits as the frame size. So basically, the block size is 48 times 2, right? So the block size is basically 2 times the frame size. So 2 times 48 is 96 bits. So each block is of size 48, right? So we know our data rate. So we know our data rate. We know our the number of bits in each block that is being transmitted. So the best time is basically the time for one block of data to be transmitted, right? So the time or the burst time is basically given by the number of bits in that particular block divided by data rate. So number of bits is basically 96 bits that is being transmitted. Remember, it is given in the question. It is twice the frame size, right? It's twice the frame size. So the frame size is 48 bits. So each block is twice this. So that is 96 bits, 96 bits long, right? So we know the number of bits that is being transmitted. We know the data rate. So our burst time is basically given by number of bits, that is 96, divided by the data rate, that is 384 kilobits per second. So our burst time is basically equal to 0.25 milliseconds, right? Then find the propagation delay. Propagation delay, uh, in this particular case, since the data is being transmitted through, right? Um, since the data is being transmitted through the air, so the burst time can be calculated. We know the speed of light. So speed of light is basically 3 times 10 to the power of 8 milliseconds. And then we know the distance that is between the base station and the handset, that is 2.5 kilometers. So knowing these two parameters, we can calculate the propagation time. The propagation time is basically equal to the distance it is going to travel, the distance divided by the speed of light, right? So in the particular case, the distance is 2,500 meters divided by 3 times 10 to the power of 8 meters per second. So that is going to give us the propagation delay, right? Or the time needed for the signal for the first signal to actually travel from the base station to the handset. So this is the time delay that is going to happen between the base station transmission of the data and the handset the handset receiving the data set, right? So the time is going to be basically equal to 8.33 microseconds. So that is our propagation time, our propagation delay, right? C, find the actual data rate on the medium. So the actual data rate formula is basically given by the actual or effective data rate is equal to two times the two times the data rate that is actually being used, two times the data rate into 1 plus propagation time plus the guard time upon the best time. So this is the formula for effective data rate, right? For transmission of the data, right? So the effective data rate is given by this particular formula. So we know our propagation delay that we have calculated in part B. We know our burst time that we calculated in part A. We know our guard time, right? So our guard time is actually given in this question, that is 0.5 milliseconds. And we know our rate, the data rate for interfacing, right? So ISDN defined interfaces provides a data rate of 384 kilobits per second. So that is the data rate that is being used, right? So we know our R value, we know our TP value, we know our TB value, we know our TT value, right? So using these values, directly substituting it into this formula, we'll get our effective data rate or actual data rate. So that is going to be 2.33 megabits per second. Moving on to the last question. A line of sight microwave link 12 kilo, a line of sight microwave link 12 kilometers long is planned for installation in Germany, which is in climate zone H. So again, we are going to use climate zone H. So as our reference, so the operational frequency is 30 gigahertz and the desired time availability of the signal is 99.99%. So it is available for 99.99% of the time, right? And the local range, just give me a sec. So yeah, so like I was saying, so the desired, I mean, the link is actually available for 99.99% of the time. So the remaining percentage of the time from the 100% is our non-availability, right? Isn't it? So it won't be available. It is the outage time. So in this particular case, it will be 100 minus 99.99. So that will be basically 0.01%, right? So the outage time is basically equal to 0.01% of the time, right? So our outage is for 0.01%. Local range statistics are not available. The antenna propagation is horizontal. Determine the amount of a total attenuation is to be anticipated for free loss space. I mean, for FSL, that is free space loss. Assume antenna gains to be equal to 1, right? So yeah. So the total attenuation is actually, since it's in a rainy climate, right? So it's actually in a rainy climate. So the total attenuation will be due to the rain and the free space loss, right? So the total attenuation will be due to the free space loss and the rain as well. So the total attenuation is going to be given by the attenuation of the rain plus the attenuation of the free space loss. So the attenuation for the rain is basically given by A times RP, which is going to give the result in dB per kilometer, right? So based on this, it says the antennas are actually polarized in horizontal. So we'll be basically using the horizontal components of the variables a and b, the coefficients a and b. So we are going to be using the horizontal components. So if we go back to this particular textbook and we see that, so our signal is actually for you can see that our frequency is actually 30 gigahertz, right? So at 30 gigahertz, what is our horizontal component? And what at 30 gigahertz, mm, what is our horizontal component for B as well, right? So going back, so this is our 30 gigahertz, right? So this is our 30 gigahertz. The horizontal components are, this is our A value, that is the horizontal component for A. And for the horizontal component of B, this is going to be our value, right? So our A value will be 0.187. Our B value will be 1.027. I mean 1.021. So once we have identified the coefficients for A and B, the next thing is to determine the rain rate, isn't it? So that is actually used for the calculation of the attenuation of the rain. So we go back to this particular table over here, right? Remember, this table is actually given in your textbook in page number 341. We go over here. Like I said, the system is available for 99.99%. So the outage will be for 0.01%, right? So, and we are looking at climate region H. So the rain rate is actually given by particular value over here, that is 32. So our rain rate is 32 millimeters per hour. Our A and B value are actually our A and B values are actually 0.187 and 1.021. So we have found our variable the values for A, B, and R, right? So that is what is given over here. That's how you determine the A value and the B value and the rain rate values, right? Okay, this is from the tables. So once you have the values for A, B, and R, we directly take these particular values and substitute it into this particular formula. So directly substituting the values, we get 0.187 times 32 to the power of 1.021. It is going to give us 6.44 dB per kilometer. So this is still not the attenuation. Remember, our attenuations are usually in strength, right, or power, or um, in decibels, right? So this is actually at the rate. So the attenuation rate is actually given over here. That is 6.44. So 6.44 decibels per kilometer. So what do we need to do? We know the distance between the transmitter and the receiver. The line of sight is basically given by 12 kilometers, right? So the distance of propagation of the signals will be 12 kilometers. So in order to find the actual attenuation, the total rain attenuation is actually given by 6.44, right? 6.44 decibels per kilometer times the distance, that is 12 kilometers. So in order to convert this particular unit dB per kilometer to just decibels, right? The total rain attenuation is basically given by the attenuation rate, right? That is over here, multiplied by 12 kilometers. It is going to give us 77.23 decibels. So we know our total rain attenuation. Now we also need to identify the total attenuation for free space loss, right? So since this particular value is in decibels, right, the free space loss formula is actually given by 4 pi d, right, holding squared divided by lambda squared multiplied by g1, g2, right? So we have to find the free space loss formula in dB. So the free space loss formula in dB is actually given by this particular formula over here. Since our antenna gains, right, as it is is given over here, assume antenna gains to be equal to 1. So in that particular case, if these two values are 1, so we are just left with 4 pi d squared divided by lambda squared. Okay, so these particular variables can be ignored because these two will give us a value of 1 times 1. So it is basically 1. So 1 times lambda squared will be just lambda squared. Now, what we can do is using the logarithmic properties, we can expand it in terms of addition and subtraction, right? If we are multiplying two variables, so it will become 10 log 4, or whatever variable we have, 10 log whatever variable we have plus the other variable, right? If we are dividing, it is basically 10 log that particular variable minus this particular variable, right? So basically using the logarithmic property. So I believe all of you must be knowing that by now, right? So in this particular case, it will be basically these two. If it's the power, you take this 2 and multiply it with the base over here, it will come in front. So 2 times 10 is going to be 20. Log, we can take 4 and pi as a constant. So that is 20 log 4 pi plus, since d is multiplied with 4 pi, so that will be plus, so plus 20 log d, right? And then this lambda squared is actually divided, we are dividing this lambda squared with this particular term over here. So again, since we have a square, so these two will be multiplied with the coefficient over here. So that will give us 20, and this negative is just because of this division over here. So that is minus 20 log lambda. Now, from this What variables do we don't know? We know the variable d, right? That is basically 12 kilometers. That is given over here, right? So d is basically 12 kilometers or 12,000 meters, right? What is our lambda? Lambda is basically given by speed of light divided by frequency. So we know our frequency, that is 30 gigahertz, right? So frequency is 30 gigahertz, and we know our speed of light. So we can find our lambda. So lambda is basically speed of light divided by frequency, that is 3 times 10 to the power of 8 divided by 30 times 10 to the power of 9. That is equal to 0.01 meters. Knowing our lambda and knowing our d value, we can directly substitute it into this particular formula to get our free space loss formula. I mean, free space loss value in dB. So evaluating this whole term, knowing our lambda and d value, we get the attenuation for free space loss as 143.56 decibels, right? So this is still not the total answer. Since the total attenuation is due to the range and the free space loss, so we have to add this. We have to add this particular value over here, and we have to add this particular value over here. That will be our total attenuation for a line of sight of for this particular system over here, right? That's being used, that is going to be installed in Germany. So the total attenuation is basically equal to 77.23 decibels plus this particular value, that is 143.56 decibels. So our total attenuation is basically equivalent to 220.79 decibels. Okay. So with that, we come to an end to our tutorial, right? So do you have any queries or anything like that? Okay, you can, everything is given over here. Just in case if you don't understand anything, you can refer back to the textbook, okay? I know at times, rather than going over this video at the end, what you can actually do is actually take this particular solution set, like you have been to this tutorial now, so you have a fair bit of idea of how it is going to be done, right? So you can just directly reflect it back to the book, and you can quickly solve this whole problem within perhaps like in 15 or 20 minutes, right? Rather than going over the whole 40 minute video. So that is why I actually encourage the other students to actually attend this tutorial, but they don't. Anyways, so with this, we'll end this tutorial session over here. Is that fine?
Okay, regarding the lab, I made out one lab. Week, I think so, lab 6. I did not submit the report. Hello?
You can hear me?
Hello? No, sir.
What I said is actually, you can.
Sir, I could not hear your voice.
Hello? You can hear me?
Yes, sir. Yes, I know.
Okay, you can submit it and just inform me, right? Just inform me and I'll.
Sir, I'll be able to submit by, after 19 because I'm in isolation at the moment. I don't have my laptop.
Just write to your lecturer and then we'll see that he doesn't penalize it, right? Because I think the mid-semester report has been already prepared, so it has to go through him now. Otherwise, if you could have submitted by this week, 19th is by when? Next week?
Next week Tuesday.
Okay, that is fine. Okay, you can submit it by next week. Because from next week, starting from next week, we'll be having projects, right? So find a group partner that you want to work with and come up with a topic. The topics are actually listed on the Moodle shell. You can select any of the topics, but it is totally up to you to propose whatever topic you want. Okay. Try to pick something that you are able to do. Don't make it too complicated or don't make it too simple, but just make it enough that you get good marks, right? I hope I'm clear with that, right? You understand what I mean?
Yes, sir. I have done a proposal. I have already submitted. It's a quadrant phase shifting, but I'm not sure whether it's right or wrong.
Yeah, I'll go over it and I'll inform that.
But I don't have a partner, sir.
If you want to work individually, that is also fine. I mean, like if you want to,
Okay, sir.
you can also work with someone. You can reach out to anyone.
Okay, sir.
So, there's Arfan. There is also Muhammad. Muhammad is also there. You can check with. I forgot about the other
Okay, sir. I will see.
those people as well, right? So
Okay, sir.
if you then is fine. If you can work alone individually, that's also fine, right? There's no harm
Okay, sir.
as long as you are comfortable with it, right? Okay.
Okay,
So
sir.
you can directly. I mean, like if you have any questions, you can directly reach out.
Okay, sir.
So we'll end this session over here, right?
Yes, sir.